In this video, we'll be talking about the different forms of energy, and we'll look at the energy in a high temperature system versus a low temperature system. So we'll go ahead and start by defining energy as the ability to do work. And we'll take a look at the different forms of energy, and we'll start on the macroscopic scale, which includes forms of energy like electrical, sound energy, and some others. And we'll mainly be looking at mechanical macroscopic energy, and this includes kinetic energy. So kinetic energy is just that energy associated with motion. Described by the equation, kinetic energy is equal to 1/2 times the mass times the velocity squared for that system or body. Next, we'll look at potential energy, and we're interested in a specific form, gravitational potential energy, and this is just that energy from the gravitational field, whether that's Earth or some other body or planets. And we'll use the equation U, which is for that potential, and then we'll create a subscript G for gravitational is equal to mass times the gravitational field strength, which on Earth is that 9.81 meters per second squared, and then times that height. Next, we'll look at energy on the microscopic scale, so microscopic on the teeny tiny microscopic, going up and down with the letters, but this is also known as internal energy. And this includes forms of energy like sensible energy. So sensible energy is that kinetic energy of the molecules, which is related to temperature. And next we'll look at latent energy, which is that energy associated with phase or state changes. And this one's a little bit less intuitive, so we'll go ahead and look at a graph for this one. So if we have temperature on the y-axis, so temperature, we'll just write it in Kelvin, and we have energy on a perfectly straight x-axis, so heat energy if we start at this solids phase, we add energy, we actually get a graph that looks something like this. And each of these slopey portions, so for example this one right here, represents a specific state. So this one is for solid, this one right here is going to be liquid, and this last one is going to be gas. And in these in-between portions, where the substance is transitioning from one state to another, this added energy is not actually increasing the temperature of that substance. And this energy right here is that latent energy. Cool, so now we'll move on to chemical energy. So chemical energy is that energy from the atomic bonds in a molecule. So these are the bonds connecting atoms within that molecule. So if you think of something like a carbohydrate, our bodies are taking those carbs and breaking them down and using that energy that's holding those atoms together, those carbon atoms together, and we're using that to do other things. Now we'll move on to a last form of energy on the internal scale or the microscopic scale. We'll look at nuclear energy, which is that strong bond energy within the nucleus. So this is the energy associated with the bonds that are connecting those protons and neutrons inside of the nucleus. That's pretty much all you have to really know. This is introductory, and we won't really dive into these specific forms into too much detail. One interesting thing to note is that for the macroscopic scale, we have that kinetic energy, and we have potential energy as well. On the microscopic scale, we have a similar thing. So we have sensible energy. So this one you could think of as the kinetic energy on the microscopic scale. And then the rest of these, so latent, chemical, and nuclear, they're kind of the potential energy on the microscopic scale. Cool. Now we'll look at energy associated with systems at different temperatures. So the system I'm about to describe is some sort of high temperature system. So this one's high temperature. And we'll look at a hot air balloon. So if we have some sort of cart right here for the person to be in, and this is the magical balloon, then if we have some sort of burner right here, and this is just the surrounding air, this is our surroundings, inside of this balloon we have some air molecules, and this burner is increasing the internal energy, the sensible energy, so it's causing these air molecules to move faster, and this increases the pressure inside of the balloon, which leads to an increase in volume. So this balloon essentially becomes bigger, and this increase in volume has the same number of molecules as before, so the air in this bigger balloon is less dense than the environment, which causes it to rise. But the main idea is that this burner right here, so this burner right here, added energy to the system and did work. So this high temperature system, relative to its surroundings, had the ability to do work. Now we'll look at a low temperature system. So relative to its environment, we'll first start out with a balloon. This time it's just a party balloon. Draw a little bit bigger for later, be easier to see. And if we take this balloon and put it inside of a refrigerator. This is a beautiful refrigerator. That's not a refrigerator. Have it in our refrigerator. And again, we have the surrounding air. So this is our surroundings, and this is a low temperature system. So this is that low temperature system. So we have some air molecules just like we have in the surroundings, but they have less energy. And we bring this balloon inside of the refrigerator. It was just in our surroundings. Now we bring it into the refrigerator. So we'll start out with the balloon like this, same size, and these air molecules are going to be inside the balloon. As time goes on, keep in mind that in the very beginning, these air molecules are moving at the same speed on average as the air molecules in the surroundings. But once it gets inside of the refrigerator, the air molecules inside the refrigerator moving a little slower on average. And so as time goes on, the faster moving particles inside of the balloon are transferring energy to the air molecules inside of the refrigerator, but not inside the surroundings. So energy is going from the balloon to the air molecules in the refrigerator. And essentially what the refrigerator does is just take this added energy and move it out into the surroundings. But what this essentially does is causes the air molecules within the balloon to slow down as time goes on. So they become slower and slower, which decreases the pressure inside the balloon, decreasing the volume of the balloon, and this causes the balloon to shrink. So after some time, the balloon will look something like that. So this outline of the balloon, that did not work at all, but it becomes a smaller version of its past self. And so what these two examples illustrate is the idea that a high temperature system relative to its surroundings and a low temperature system relative to its surroundings both have the ability to do work. So these both have that ability to do work. Thank you for joining me on this video. I'll see you in the next one.